We now treat algorithms from mathematical optimization. This is a very common problem, as we will see with many examples to come. The basic notion is that you have a set of variables, x1, x2, up to x sub n, n of them, which together form what I will call a tuple x, an n-tuple. And the idea is that we're given a function f sub 0, which gives a scalar value for every value of the tuple. And we're looking for that value of the tuple such that f0 is as large as possible, maximizing. We'll later talk about minimizing a bit, but there's really not much to say. If you have to minimize f sub 0, you can say maximize minus f sub 0. Now, sometimes this problem is, we've done describing it, it's unconstrained. But frequently there are constraints, f sub 1, f sub 2, up to f sub m. So f sub 1 is another function of the tuple, gives a scalar, and we may require that f sub 1, that the x that we're interested in must satisfy that it's less than or equal to b sub 1. And moreover, we may have another function, f sub 2, that says the x tuple has to also satisfy f sub 2 of x is less than or equal to b sub 2. And we may have m such constraints. Then we have this so-called constrained optimization problem. So we're trying to find that particular tuple, that particular value of the tuple, that is to say a value for x1 and another different value for x2 and a different value for x3 and so on up to a value for xn, such that among all tuples which satisfy the constraint, this one, which we'll call x star, has the largest value of f0. Examples of problems like this. So we have a list of assets, and an x1 is the amount we have invested in asset 1, x2 is the amount to be invested in asset 2, and so on. And the constraints may be we have a total budget, so the sum of the amounts may have to be less than or equal to some budget level. We may be unwilling to invest more than some particular amount for each asset. We may be unwilling to invest a tiny amount, so we may have a minimum amount of investment per asset. We may be willing to only accept solutions that have some minimum total return. The objective then function, we could want to maximize the return or maximize the overall risk, or minimize the overall risk, probably more likely. In another example, device sizing in electronic circuits, we may be trying to design a chip, and we know that the wire widths and the wire lengths are the major things that matter. and we may have constraints on how wide something we can that we can manufacture something no wider than such and such, no less than such and such. We probably will have a total area that can be covered by the devices. And within those constraints, we want to minimize power consumption. In many problems, we have multiple parameters of some model, and the model, for example, may be a quadratic with three parameters. The quadratic would be of the form a plus bx plus cx squared, and a, b, and c would be the parameters, the things we had called x. That's not the x, that's the variable x of the polynomial. It's the tuple, the thing we're calling x here is the tuple of coefficients. Perhaps I should have called it a plus by plus cy squared to not confuse the argument of the polynomial y with the parameters a, b, c, which are the x, the so-called x. We may, for example, have limits on what the parameters are. So a may necessarily be positive, for example. And the overall objective is a measure of how well the polynomial fits a bunch of measured points. So we see in the diagram the dots are a bunch of measured points, and we're trying to fit a curve through those measured points. All of these are examples where we're trying to do optimization. Is very heavily used. There are all sorts of algorithmic packages. There are thousands of papers on even a single class of methods. There are hundreds of books. There are lots of courses. They tend to fall in the area that's called operations research. But within the computer science department here, we teach a course on optimization. There are hundreds, or in fact thousands probably, of companies that provide consultation on optimization, and essentially every type of business, like the ones listed here, makes serious use of optimization. For example, the airlines want to minimize fuel consumption, subject to constraints on the time taken to get from one place to another. Or they may want, and they may want to, the variables that they may want to optimize is the altitudes at which they fly for various parts of the trip. Concerned with methods for solving them, for finding the optimization, finding the optimum in question for a given problem with a given objective function and given constraints. But the general optimization problem for arbitrary F0 and F1 through Fm is very difficult to solve. They may take extremely long computation time, or they may, if you limit the computation time, not always find the optimum that you're looking for. In my own research, I'm concerned with finding an object in a medical image. It's called object segmentation. For example, in a CT image, the 3D image, one may be interested in finding a particular organ, say the liver. In other situations, we have an organ that's deforming, and we're trying to characterize the deformations by asking what deformation of one image makes it close to another image. That's the image registration problem. Both of those are normally posed as optimization problems. We want to find, for example, the particular form of a liver in a CT image which is most consistent with the CT image data, but as constrained by it being adequately liver-shaped. However, even though the general optimization problem is very difficult to solve, and indeed the above problems that I've been talking about, we do not have general algorithms that always find the optimum. Certain problems can be solved efficiently and reliably. So a least squares problem can indeed be solved, and we'll see how. Problems where the objective function is linear in the x variables, and where each constraint is linear in the x variables, produces what's called a linear programming problem, and those can be solved, and we'll be spending the majority of our time in this set of lectures on the linear programming problems. There are other nonlinear programming problems where the space, where the objective function over the space is convex. That is to say, it has a single optimum. And there are nice algorithms for dealing with them as well, although we'll not be talking about them in this course. So let's talk about the convex optimization problem. So say we have a set of variables x. In the example here in the figure, the x has three variables, x sub 1, x sub 2, x sub 3, or equivalently x, y, and z, as we normally think about it. And we have this function f sub 0, which we can evaluate at any x, y, z tuple. If the region that's consistent with the constraints is convex, which I'll define in a moment, then we have an ability to solve the problem. Because basically, if we orient our object so that up is in the value of increasing values of f sub 0, we're simply trying to find the top point on the boundary of this convex region. A problem we can solve. The convex formulation says that for each one of the f sub i's, if you have a function of, well, here, one x tuple, x means x, y, z, x1, x2, x3, y means y1, y2, y3. So we have 2 points, x and y, and we have a linear combination of them where the sum of the weights alpha and beta is 1. In other words, we have any average between the point x1, x2, x3 and the point y1, y2, y3. There's a line between those 2 points in 3 space, and a line segment actually, and it starts at x1, x2, x3 and ends at y1, y2, y3. And if for every place on that line, the value of the constraint function is less than or equal to the average at the 2 endpoints, at x and at y, with the same weighted average, same weights, alpha, beta, then that's a convex problem. And we will see that least squares problems are always convex, and these linear program problems that I spoke of are always convex as well. Indeed, the figure here in this slide is a constraint space corresponding to these linear constraints that where the constraints together produce a convex polyhedron. Convex optimization is solvable, but frequently there's no analytical solution. We can't write down an equation in terms of the variables in our constraints and the variables in our objective function. Instead, the problem typically is solved iteratively. And there are reliable and efficient iterative algorithms for doing that for convex optimization. So if we have n variables, that is to say we are the x has x1 through xn, we frequently concede that the amount of time is proportional to the larger of the cube of the number of variables, the square of the number of variables times the number of constraints, or the cost, if we have expensive f sub i's, f sub 0, simply the cost that if that's very expensive, then the cost of evaluating all of them and their first derivatives and all their second derivatives, that is to say the first partial derivatives with respect to x1, x2, up to xn respectively, and all the second derivatives with respect to an xi and an xj. There are lots of algorithms for doing this. It's sometimes difficult when you have an initial problem to recognize whether it is convex. But there are many interesting ideas for transforming problems into convex form. And our graduate course, COMP 777, in fact, focuses on these approaches. The result is that surprisingly many problems can be solved via convex optimization because if it didn't originally seem or convex or wasn't, you can turn it into a problem that is convex. Let's look at the least squares problem. In the simplest form, we have big N linear equations in little n unknowns. So x is a tuple, x1 through xn, as before, and we have capital N linear equations in those little n unknowns, and there are, let's say, more equations than unknowns. And so no particular value of the tuple x can actually solve all big N of the linear equations. In that case, we will consider the linear equations to be represented by a matrix whose rows are the coefficients of the x values and whose corresponding b values are the right side of the equation. And we'll look at the residue, the difference between ax minus b for the first equation, and then for the second equation, and then for the third equation. So we will get big N of these differences. Ax minus b is a big N tuple of differences. If we take the sum of the squares of those difference values, summed over the capital N equations, we get the mathematical form that you see there, the L2 norm squared of ax minus b. Using the L2 norm is just the Pythagorean sum of squares. Well, the square root of the sum of squares, and the square of it is the sum of squares. So we then have this sum of squares which we want to be as small as possible. We have a minimization problem. In some other situations, we have a set of so-called basis functions. An example is a polynomial, of quadratic polynomial, which has the basis functions 1. Let's call it a polynomial in y. So it has 1 and y squared. And so any particular quadratic in y is a times 1 plus b times y plus c times y squared. That is to say, we have to find the values a, b, and c that are best. So these phi j of y functions are these basis functions. So in our example, we have 3 of them, and phi sub 1 is 1, and phi sub 2 is y, and phi sub 3 is y squared. And the coefficients, what we called ABC, are now the things we're optimizing over. So those are our x sub j's. So any polynomial will be the sum over j of x sub j times phi super j. And when evaluated at some particular value of y, you will get a particular, the evaluation of this quadratic, x1 times 1 plus x2 times y plus x3 times y squared at that particular value of y. Now let's assume that we're given a bunch of values of y. For the first yi, we are told that the value is b1. So for y1, the value is b1. For y2, the value is b2. In the diagram, y is on the horizontal axis, the so-called abscissa, and along the vertical axis, which is called the ordinate, we have the b values at each specific yi for which we have measurements. And so what we're trying to do is to get the polynomial value to be at any given each of those yi's to be as close to bi as possible. And so we're going to sum over all the yi's the square distance between bi and the weighted sum of phi j of yi's, which is the polynomial value. Both of these problems that we have talked about, the ax minus b differences squared, or the b minus the polynomial value difference squared, have the same form. That you want to minimize the sum of square differences over the values xj, which are on the second problem, the coefficients. So we want to be able to solve this kind of least squares problem. And we can show that there is an analytic solution. For those who know linear algebra, you can take the transpose of the matrix. This is for the linear equations problem. We can take the matrix capital A and transpose it, multiply it by A, take the inverse, multiply that by the A transpose matrix, and that by the B tuple, and we will get, indeed, the optimum. So there is an analytic solution. We can show that the other problem, the one with basis functions, can also be solved by solving a set of little n linear equations in little n unknowns. And we'll not detail that except to say that this analytic solution gives reliable algorithms and gives computation time that is polynomial. Least squares problems are really easy to recognize, and there are a bunch of techniques to make the solution a little bit less sensitive to outlier measurements, for example. But we can solve those problems by solving linear equations, and we'll not go further in discussing least squares here. Instead, we're going to move on to the linear programming problem. Here, we have a constrained optimization, as described before, and we have an objective function, as described before, but both involve linear weighting of the optimization variables x sub I. So the objective function that we want to maximize is sum of c sub I, x sub I, and we're given the c sub i's. c1 times x1 plus c2 times x2 plus cn times xn is a value that we can evaluate. and we're trying to, given the c's, to find the x's that optimize that objective function. But we're also given constraints, and each one of them is linear in the variables too. That is to say, each one is of the form, the first constraint is of the form sum a sub 1j xj is less than or equal to b sub 1. That is to say, a11 x1 plus a12 x2 plus a13 x3 plus a1n xn is less than or equal to b1. And the same for the I equals 2 cases with a21 times x1 plus a22 times x2 and so on, which is going to have to be less than or equal to b2 for m such constraints. Or the constraints can be equality constraints. So instead of saying it's less than or equal to b1, we can constrain it to be equal to b1 for the first case. And the second one may be a greater than or equal constraint, that a2j xj is greater than or equal to b2. Let's say sum a2j xj summed over j is greater than or equal to b2. There are lots of examples of problems that have these linear objective functions and linear constraints. We want to optimize production. Production is a linear combination of the amounts of each manufactured item that we will produce. And we have a total budget that we have available, and that budget is also a linearly weighted sum of the amounts of the individual items times their cost. Or we may want to minimize the cost, and we have constraints on the production, and that's similarly linear. And we have also looked at quite a few shortest path problems on graphs, and the total weight of a path is the sum of the weights on that path, which is a linear combination of those weights. And if you want to optimize over all paths, we may have an objective function, which is the sum of the weights over all paths. And we may have certain constraints on which paths are allowed. We've seen that in our discussion of our shortest path problems. To make this problem of linear programming concrete, let's look at an example. The example is a pie eating contest, and the total time is 1 hour, and that's the constraint. And you have two kinds of pies that you can eat, a torte that takes 2 minutes and an apple pie that takes 3 minutes. And you get 4 points in this contest for a torte and 5 for each apple pie. So the question is, what should this contestant eat so as to get the most points? So the way you solve this problem is decide what the decision variables are and what their weights are. The two decision variables will be how many tortes that should be eaten, x sub 1, and how many apple pies that should be eaten, x sub 2. And the weights are 4 points per tort and 5 points per apple pie. And so the objective function that we're trying to optimize is 4 times x1 plus 5 times x2. The constraint is the time. That is to say, 2, that is to say the number of minutes to eat a tort, times the number of torts, plus 3 times the number of minutes to eat an apple pie, has to be less than or equal to 60. In this particular example, there's one constraint, but in the general problem, there may be multiple constraints. Solving this problem can be understood geometrically, and doing so will clarify what's going on. So in 3 space, n equals 3, we have x sub 1, x sub 2, x sub 3, which we might think of as x, a y, and a z. And so any x1, x2, x3 tuple is a point in 3-dimensional space. In general, if you have n x sub i's, the tuple can be understood as a point in n-dimensional space, but that's a little bit hard to visualize. So we will keep our visualization for now to 3 dimensions. So n equals 3. We will be concerned about distances between points, one particular tuple x1, x2, x3, and a different point, let's call it y1, y2, y3, in the same space, and we will assume that the Pythagorean theorem applies to compute the distance. So we can take the distance y1 minus x1, square it, take the distance y2 minus x2, square it, take the distance y3 minus x3, square it, sum the squares, and take the square root of the sum of squares, and that will be our distance between the 2 points. In this, okay, so we are going to be given an objective function. We're trying to optimize, and let's assume that we have organized our 3D space so that it's oriented not along the z-axis, but along the direction where up is higher of our objective function. Now we have these inequality constraints, m of them. Each less than or equal to constraint, we'll worry about the equal ones later, but each less than or equal to constraint says that the point has to be on one side of some plane. Likewise, each greater than or equal constraint says that the point has to be on the appropriate side of that plane. And if you put all the planes that together, each constraint will be a plane constraint, but when you intersect them all, you get this polyhedron that is shown here. So, and this polyhedron is not only any old polyhedron, but it's convex. So what we can say we're trying to do, once we have this polyhedron oriented so that up is higher values of the objective function, we're trying to find the top place within or on this polyhedron. But of course, places on the polyhedron, if there's a place in the polyhedron, there's another place a little higher than on the surface of the polyhedron. So we'll be able to consider the places that on the surface of the polyhedron and try to find that place which maximizes f sub 0. Moreover, we can intuitively see that the top is going to occur at some vertex of this polyhedron. Let's understand this polyhedron better. The polyhedron bounds a region of space in its interior. The interior, as well as the points on the boundary, are places where all the constraints are satisfied. The boundary itself are places where you switch from the constraints being followed to the constraints not being followed. And assuming that our constraints are all of the less than or equal or greater than or equal form, these faces are places where the equality holds. In 3D, what this means is you have a convex polyhedron, and you can understand that a convex polyhedron has 2D faces, planar faces. A plane is a two-dimensional entity. If you look at a plane, you can consider two coordinate axes for the plane, and any place on the plane can be specified as so much of one coordinate plus a different amount of the other coordinate. It takes two numbers to describe a position on a plane. Thus we say a plane is a 2D entity embedded in 3 dimensions. The intersection of two planes forms a line. These are the edges. They are one-dimensional. It only takes one number to say where you are along a line. These are where the faces intersect. And when 3 faces intersect, or equivalently when 2 edges intersect, you get a 0-dimensional entity, a point. And those are the vertices. We have to use our imagination to extend this idea to n dimensions, where we have not 3 optimization variables, but n of them. Now the faces, well, the overall object, first of all, is a hyperpolyhedron, bounds a part of n-dimensional face, and it's bounded by n-1 dimensional hyperplanar faces. So faces that are 1 dimension lower than the dimension of the space. And they intersect, these hyperplanar faces, in n-2 dimensional subhyperplanar subfaces, which in turn intersect in n-3 dimensional subhyperplanar subfaces, and so on, down to the point where n-1 of the original hyperplanar faces have intersected to form a 1D line, or equivalently, two of the 2D faces that were formed by these successive intersections have been, these are ordinary planes now, have intersected to form a line, which, as we saw in 3D, two of the lines intersect in a zero-dimensional vertex. Now, let's consider this hyperpolyhedron rotated in such a way that up corresponds to the direction of increase of the objective function. That is to say, the higher the point is, the greater the objective function is. It should be intuitively clear that the maximum will occur on the boundary of this hyperpolyhedron, and indeed at a vertex. Well, not necessarily at a single vertex. It may be at a single vertex. But if, for example, one of the lines is equally high all along the line, anywhere on that line segment will be the optimum. But therefore, the vertices at the ends of that line segment will be optima. And so there is at least a vertex at which the optimum of the objective function is taken. Similarly, a face may be parallel to the it will be to the axis of up. Let's see, maybe orthogonal to the axis of up. That is to say, all the places on the face are places where the maximum occurs. But again, the face includes vertices. So in any case, there's always some vertex, sometimes multiple vertices, where the optimum is taken. And the result is that we don't need to consider any places but vertices to find the optimum. And that is the basis for the general form of the algorithm that we will be considering, which involves moving from vertex to vertex along the edges, and at each step moving only along an edge that increases the objective function, until we eventually come to a vertex that is at the top. We have said that assuming each one of the constraints is of a less than or equal or greater than or equal form, that the planes, the hyperplanes, corresponding to the equal states are the extremes of the constraints. That is to say, on one side of the hyperplane, the constraint is in effect, that is to say, those points follow the constraint. And on the other side of that same hyperplane, the constraint does not apply. The points do not follow the constraint. So these hyperpolyhedron faces are the extremes of the constraints, where the constraints change from not being followed to being followed. Now let us consider the intersections of those hyperplanes. Each hyperplane corresponds to a constraint extreme, and when you have intersections, you have the extreme of more than one constraint. In particular, when two hyperplanes intersect, then you have two constraints being followed on one side of the intersection and neither on the other side. An example is in 3D, which the figure illustrates. You see this line, look at the vertex at the left end of this line and the line that it consists of, that it ends. The line is simultaneously in the top face and in the face facing us, and so it corresponds to the extremes of both the top face and the facing face. The vertex on the left adds the left side facing face to the constraint. And then all three of those constraints apply. So, well, in n dimensions, the extension of this idea is that a 1D edge is the intersection of n minus 1 of the constraints. Each constraint lowers the dimension by 1. And a vertex, a point, is the intersection of n of the constraints, or n of the constraint extremes to be more precise. Thus, when you move from one vertex to another vertex along a line, you have a situation, let's say at the left end of the line in the intersection, where n of the constraints apply. As you move along that line, the extreme of one of the constraints is released, and you are still within the constraint, the less than or equal or greater than or equal constraint, but no longer in the equal of that constraint. You're in the less than or greater than part. And then as you move to the other end of the line, the other vertex, you pick up the extreme of a different constraint. As you walk along the line, n minus 1 of the constraint extremes stay in effect, and you're swapping one constraint extreme from the other to the other by moving from one vertex to the next. This will be the basis for the idea of the simplex algorithm for solving linear programming problems, whereby we move from one vertex to another in a way to increase the objective function. And in doing so, we have a constraint extreme that we're leaving and a new constraint extreme that we are picking up. We have finished our general introduction of the linear programming, and the next video will take us into how the algorithm actually works to allow us to find vertices and move along edges as described. And there'll be lots of algebra there. For the time being, though, I want to talk about the general optimization problem again. We saw that there were sometimes unconstrained optimization problems. Linear equations were, least squares was an example of such an unconstrained optimization. And for that one, we could solve the problem analytically. But in general, if it's not a least squares problem, you may need some method for iterative optimization. Similarly, there are these problems of constrained optimization with not necessarily linear objective functions and constraints, in which case there's a method called Lagrange multipliers that allows you to turn the problem into a higher dimensional problem of unconstrained optimization. And then we can use the iterative methods for that. Sometimes the objective function is quadratic in the optimization variables x1 to xn. That is to say, it involves terms like x1 squared and x2 squared, but also terms like x1 times x2, but only products of 2 or 1 or 0 variables are involved. That engages a set of techniques called quadratic programming that we won't go into. We're talking about linear programming, where the objective function and the constraints are linear in the optimization variables. There's also 0-1 programming, where the x values can only take on binary zeros or ones. And there's things called integer programming, where the solutions are only allowed to be integers. And for each, there's a whole collection of algorithm possibilities that you can learn about if you take appropriate operations research course in our STOR, Statistics and Operations Research department. For the particular optimization problem on which we're focusing, namely the linear programming problem, there are multiple algorithms that have been invented. Some of them are guaranteed to operate in polynomial time, and some of those are practical. The particular algorithm that we're going to cover is the simplex algorithm, which was invented in 1947. It is, for most practical problems, an algorithm that runs in polynomial time, but it's not guaranteed to be in polynomial time. There are problems with nonlinear programs where the bounding surfaces of the region are not flat, they're curved, that whose solution can be generalized from one of these ones that works for linear programming, but then they're not known to be in polynomial time. We have a few more matters to make clear in setting up the linear programming problem. In general, we have a problem where we have a linear combination of the optimization variables x1, x2 up to xn that form the tuple x. And we have a weight tuple, C1 to Cn, and linear algebraically, if C forms a column vector and x forms a column vector, the weighted sum C1 times x1 plus C2 times x2 plus ... plus Cn times x1 can be written as C transposed times x. And that's subject to the constraints, and we've said that each one of them can be of the form a sub I1 x1 plus a sub I2 x2 plus ... plus a sub I n xn less than or equal to b1, or greater than or equal to some b1. For the time being, we'll not consider the equality constraints, but we'll see that we don't need to shortly. And there are m of these constraints, each with its own weight tuple A. So each of the constraints can be written as the AI n tuple transpose times x less than or equal to b sub I. If it's greater than or equal to, we will see that we can transform this into less than or equal very, very simply. And we're assuming that all the solutions are of the all the optimization variables are necessarily non-negative. And again, we can transform the problem in a way we will describe if that's not the case. So now we have this so-called canonical form, minimize C transpose x subject to, for I equals 1 to m, a sub I transpose x less than or equal to bi, and all the elements of x are non-negative. This is the form we will talk about solving with our linear program, our simplex algorithm that we're going to be talking about. There's no analytical formula to solve this, but we are talking about a problem that there exist reliable and efficient algorithms and lots of software for doing it. With good computation time, polynomial computation time, this is a technology that is very mature, fully documented in web resident programs. Seeing that a problem is in this form may not be so easy as, for example, a least square problem, but it nevertheless can be recognized. And as I said, the general problems that that once you recognize it will not necessarily be in the canonical form, but there are the tricks that we will be talking about in a moment that convert the problem into canonical form. Now let's consider the function C transpose x, or sum over I, C sub I, x sub I. That's f sub 0. And its level sets, that is to say places where f sub 0 is some fixed value, are hyperplanes orthogonal to the vector direction c. Thus, increasing f sub 0 involves moving the hyperplane along this vector direction c. And then the optimum is the intersection of the farthest along plane, orthogonal to c, with the constraints polyhedron. And we have understood that that intersection must include some vertex which the algorithm tries to find. Before we show how to convert the problem into canonical form, let's understand it, that form in 2D. So we may have a function z equals minus 2x1 minus 3x2, subject to the three constraints that are written: x sub 1 minus 2x2 less than or equal to 4, 2x1 plus x2 less than or equal to 18, x2 less than or equal to 10, and x1, x2 greater than or equal to 0. And let's assume that what we're trying to do is minimize that. If we look at the function that we're minimizing, minus 2x1 minus 3x2, we can move from the origin to in the direction minus 2 comma minus 3. And that gives the direction of increase, greatest direction of increase of this function. And so if we wanted to maximize minus 2x1 minus 3x2, we would move down and to the left. And if we want to minimize, we'd want to move up and to the right along that vector direction. If we took z and looked at a new z, which is minus the old z, then we'd go in the direction 2, 3. The vector would be reversed, and the maximum would occur at the circled point in the upper right. The red line with the arrows at the ends indicates one of the, we called it hyperplanes, but in 2D it's simply a line that has been moved up and to the right. It's a line orthogonal to the objective function vector and moved up and to the right so as to minimize the original objective function, or equivalently maximize 2x1 plus 3x2. The white space is the polyhedron, in this case polygon. Each of the lines corresponds to one of the constraints as marked. Notice that both x1 and x2 are greater than or equal to 0. The origin is at the lower left, and the x's are the region is bounded by x1 equals 0 and x2 equals 0, and has to be to the right of of the vertical line and above the horizontal axis. And the three constraints correspond to the the line bounding the top of the hyperpolyhedron, that's x2 less than or equal to 10. The line bounding the lower right of the polyhedron, that's x1 minus 2x2 less than or equal to 4. And the line bounding the upper right of the polyhedron, that's 2x1 plus x2 less than or equal to 18. strictly speaking, the lines bounding the region where the constraints are met are the equality form of the less than or equal to constraints. We have actually 5 constraints. One, that x1 was greater than or equal to 0. That is to say, it's to the right of the x2 axis. Another one, that x2 is greater than or equal to 0. It's above the x1 axis. And the other with the 3 specified given constraints. Now let's assume we're at some vertex of this, of the boundary of this polygon, this polygonal region. So we're, and in particular, let's assume that we are at the vertex which is along on the x1 axis and as far to the right as the white region goes. At this vertex, 2 of the constraints hold in extreme. We have that x2 is equal to 0. That's one of the extreme constraints. And we also have that at that place, x1 minus 2x2 equals 4. The other constraints, the constraint on x1, x1 is greater than 0 there, not equal to 0. Likewise, the constraint corresponding to the diagonal line corresponding to 2x1 plus x2 equals 18 does not hold as equality, as extreme, but rather 2x1 plus x2 is less than 18. It holds, but not in extreme. And likewise, x2 is less than 10. So 2 of the constraints hold at that vertex and in extreme, and the other 3 hold, but not in extreme. As we move along the line, the x1 minus 2x2 equals 4 from the vertex, we see that we are lowering the value of the objective function. That is to say, the component of our motion is opposite to the direction of increase. And since we're trying to minimize in this example, that's the direction, that's how we want to go. And so we're going to move along that line segment from the vertex that's on the x1 axis to up and to the right until we reach the extreme of the 2x1 plus x2 less than or equal to 18 constraint, namely the place where 2x1 plus x2 equals 18. At that point, we satisfy the 2x1 plus x2 equals 18 extreme, but we no longer are satisfying the x2 equals 0 extreme. We have an x2 greater than 0 situation there. So we've swapped one extreme constraint from another. Once we're at that vertex, the one farthest to the right in the diagram, we can march along the new edge, which also has a component of minimizing with regard to the objective function, until we reach the extreme of the x2 less than or equal to 10 constraint, namely the line x2 equals 10. And at that point, we now have the x2 equals 10 constraint holding, and still have the 2x1 plus x2 equals 18 constraint holding, those two constraints. But the other three constraints are in their less than form holding, but not in extreme equal form. And indeed here we have reached the optimum that we're after. And so this is the general idea of our method. That is to say, we're going to start at some vertex, march along edges that move us towards the minimum or maximum that we want, until we come to a new extreme constraint that cuts us off. And then at that point, we switch to an edge along the new set of holding constraints until we've swapped for another constraint by reaching the bounding, and so on. Ready now, finally, to talk about how we transform our original problem into canonical form. Let's remember what the canonical form is. It is maximize C super T x, subject to constraints that are less than or equal to constraints for the given constraints, and are greater than or equal constraints for the x variables, that is to say, the optimization variables. And so for some C, we want to optimize CTX, for example, that the weights 7, 5 give you a greater than or equal to 7. Let's say we're given that, and x1 and x2 is greater than or equal to 0, and somehow we really want it to be in the form something is less than or equal to 7, so that we can work with this canonical form. So here is how we can transform the problem into canonical form. First of all, we want to be a maximization problem. If we had a minimization problem, we can simply change all the coefficients to their negatives in the objective function, and then it becomes a maximization problem. We've seen that in our example. Secondly, we want all the variables to have non-negativity constraints. We can play the following game. If we have some particular variable, x sub 2, that, or some x sub I, that has no constraint, we can create a new pair of variables, call them x sub n plus 1 and x sub n plus 2, each with a non-negative constraint, and where x sub n plus 1 minus x sub n plus 2 is equal to the old x sub I. Variables that have a constraint, but not in the non-negativity form, can either be, if the constraint is in the less than or equal direction and we want it to be greater than or equal to, we can replace the variable by its negative. And if it's value is to be less than or equal to some non-zero value, we can subtract that non-zero value and create a new. So if we had x sub 3 less than or equal to 4, we could rewrite that as x sub 3 minus 4 less than or equal to 0, and have a new variable which is x sub 3 minus 4. And now, since we want it to be greater than the constraint, we could take the minus of that and have this be the variable that we actually work with. We said we were concerned with equality constraints, and we really only want inequality constraints. But equality is the combination of something being less than or equal to the specified value and greater than or equal to the specified value. And so if we have a constraint of the form A sub I transform x equals B sub I, we create two constraints that replace the old constraint. One of the forms A sub I transpose x is greater than or equal to the specified value, and the other A sub transpose x is less than or equal to the specified value. And having done that, we have no more equality constraints, only less than or equal and greater or equal to. And then, since we want all less than or equal constraints, the greater than or equal constraints can be changed to less than or equal constraints by multiplying the whole constraint through, on both sides of the equation, if you will, by minus 1. Well, once it's been formed greater than or equal to 0, you're only multiplying the left side. The minus 1 times 0 is 0. We have shown how to turn any linear programming problem into canonical form. And we see the form here on the left, maximizing C transpose X subject to less than or equal to constraints for the given constraints and positivity constraints on the optimization variables. The next transformation we make is to what's so-called standard form, where with the use of something called slack variables, additional variables that we add so that we will have one new variable per original constraint. And with the use of them, the constraints are turned into from AX less than or equal to B to AX equal B. We will see how that works now. Is that on the extreme line for a constraint, the constraint extreme holds. But as we get away from that line, but are still in the constraint holding region, just not at the extreme, the difference between the line and the position we're at in regard to that direction, the distance is not equal to 0. And we're going to create a new variable for that constraint that measures the difference between the value that holds on the extreme and the present value. So take our example of the constraint 2x1 plus x2 equals 18. That holds everywhere along the line, the diagonally pointing upwards on the right side of the constraint region. But as we get away from that, say along the edge, the downward facing edge on the lower right, as we get away from the corner, that constraint, it still holds that 2x plus x1 plus x2 is less than or equal to 18, in particular, except at the corner, less than 18. And we will create a variable that's the difference between what the value is on the line, namely 0, if we take 18 minus 2x1 plus x2, and some lower but positive value. And we'll call that value, this difference between the constraint at the extreme, which is now going to be 0, and what it is here, a new variable y sub 1, which we call a slack variable. Once we have that slack variable, the constraint can be rewritten as 2x1 plus x2 minus y sub 1 equals 0. So we replace the constraint 2x1 plus x2 minus 18 less than or equal to 0 to 2x1 plus x2 minus y1 equals 0 by creating this new slack variable y1 that simply says the difference from the 0 situation. For each one of the constraints, we now have the problem transformed from canonical form to standard form. The problem is still to maximize. We now have, if we had m constraints and n original variables, we now have n plus m variables, all the original x sub i's, and the slack variables y sub 1 to y sub m. So x sub 1 to x sub n and y sub 1 to y sub m. We'll think of that as a new x tuple that is n plus m dimensional. The maximization C transpose x is the same, except that the C transpose has to have n plus m items, and since the weights on all the slack variables, they're not involved in this objective function, so we'll simply have 0 weights for the last m entries into C. And now with the slack variables included, we now have AX equals B constraints, and still positivity on all the x's. This standard form is the form that the simplex algorithm that we will be discussing in the next video uses. So to summarize, the overall original linear programming problem is going to be dealt with by finding vertices and edges and moving along along edges from vertex to vertex in a way to, if we're maximizing, successively increase the objective function, and eventually getting to a vertex that is the maximum, and that we're going to accomplish this with an algorithm called the simplex algorithm that requires us first to turn our problem as given into canonical form by the methods we specified, and then using slack variables, one per constraint, to change the problem into a problem of n plus m variables with equality constraints. Here we have a worksheet for you to pass in on the due date for this video. And here we have exercises that we will do in an inverted class on that starting on that due date.